Okay, so it's a pleasure to have Behrooz Mirzaii, and he will be speaking about the homology of general linear groups over local rings.
First, I'd like to thank the organizer, especially Sam, for the invitation and for giving me this opportunity to present my work. Well, as you can see from the title, it's about homology of general linear groups over local rings. The talk will have a more algebraic nature, but for some of the problems solved here, they are algebraic geometric, algebraic topological approach, and some of them are very deep. When I am there, I will talk about them. I will start with some history. I hope it's not get boring with this part because I don't know the background of all the audience. So general linear groups over a ring are everybody knows of rank n. They are all invertible matrices, n by n invertible matrices. And En is En of R is a subgroup of GLN is generated by elementary matrices. We have usual relation entry between elementary matrices, and we can, for example, we can immediately say from the C that the elementary group ENR is a perfect subgroup for n positive. In general, En is not normal in GLNR for a general ring, but there is a famous theorem of Sustain, which this is the case when R is a ring. And so En is a normal in GLNR for n greater or equal to 3. We have usual embeddings. We can embed GLN in GLN plus 1, the same for elementary matrices, and we can construct the stable linear group and stable elementary group. And we have the very famous lemma of Whitehead, which says that the elementary group, the stable elementary group of R is the commutator subgroup of the stable linear group, GLR. So, well, we have an example that this is not the case for elementary groups En. For example, we have example for van der Kallen, which elementary, the fourth elementary group of the ring that you can see here is not the commutator subgroup of GL4. So we have this first K group and phase unstable K groups, which is simply GLR over ER, the elementary subgroup, this is the first homology of the group GLR. And we have the unstable versions, K1 and R, which is defined the same way. So only that we should note that this is not a group in general. If it is, this is not commutative in general. So we have the first stability for K groups. Well, it started for K0, but I'm stating for K1 and K2. If R is a ring with finite stable rank, then Bass proved that we have the surjective map from K1 n and R to K1 n plus 1 R. This is the unstable version when n is greater than or equal to stable rank of R. And Bass and Westerstein proved that this is injective or bijective when n is greater than or equal to stable rank plus 1. And we have Milner K2. This is the historic way how the K2 was defined, and which is second homology of this the elementary linear groups. And we have an unstable version, which is K2n of R, which is again second homology of E and R. And we have K2 stability, which is the proof is a bit involved, where it has a lot of generator relations. And so if R is a ring of finite stable rank, SRR, then Dennis and Washline proved that we have this projective map of K2n to K2 of n plus 1 when n is larger than or equal to a maximum of 4 and stable SR plus 1. And we have the bijective version of Sustain, Bayev, and Van der Kalm, which this is injective or bijective when n is greater or equal to maximum of 5 and SR plus 2. Well, I had the notion of stable rank here. Probably I can skip this part, but let's be fast here. A vector in Rn is called unimodular if the sub module generated by it be a free summand of Rn. So if Rn is the set of all unimodular elements of Rn, we set UR as a set of all unimodular elements of Rn. So we say R satisfies stable range condition Sm if for any unimodular element of R m plus 1, like I0, R1 to Rm, there exists elements T1 to Tm in R such that this vector presented here be unimodular. So, and R has a stable rank M if M is the minimum of all K, which Sk is Sk holds. In this case, we write that SR of the ring is M. If such an element does not exist, we say it's infinite. So, and famous theorem of Bass says that if R is a commutative ring of Coulomb dimension D, then stable rank is less than or equal to D plus 1. So this was a history of on homological stability until we have this famous unpublished work of Koilen, which when F is a field with more than 2 elements, then we have this homology stability for GLN of F. So I's homology of GLN, the map from I's homology of GLN to I's homology of GLN plus 1 is surjective if n is greater than or equal to I, and is injective if n is greater than or equal to I plus 1. This was unpublished for many years. The proof was unavailable for many years, but later the Koilen's hands notes were available online, and a published now proof of this is part of the follow-on paper that you can see here on homological stability of classical groups. But of course, Spern and Val go beyond the linear groups, and they prove the case, other cases too. But if you want to see the Koilen's proof, you can find in this article. So this is I was wondering when I remember that back in 2000 when I was working on the homology stability problem, I was wondering if the same thing is true for local rings when the residue field is more than 2 elements. I don't know if there is any result in this direction, or is there any counterexample to that, but I think it's interesting to study this case too for local rings, if such a general result is true for local rings. The first theorem, which is very general in relation to homological stability, is to Van der Kalm, which says that the I's homology of GLN to I's homology of GLN plus 1 is surjective if n is greater than or equal to 2I plus E plus minus 1, which E is maximum of 1 and a stable rank of R minus 1. And the same map is bijective if n is greater than or equal to 2I plus E. This was later generalized by Suslin. He got better bounds, and you can see the bounds that he got here. It's surjective if n is equal to maximum of 2I plus SR R plus I minus 1, and is bijective if n is greater than or equal to maximum of 2I plus 1 and stable SR plus I. Sustain's proof is a bit different. He used part of Van der Kallen's work, especially the poset of unimodular vectors, which he studies. But his proof is a bit different. He first proved homology stability for K groups, and then from that he proves for general linear groups. So let's go to back to K2 of F. We have this famous theorem of Matsumoto, which gives a generator and relations for K2 of F. And this inspired Milnor to define Milnor K groups. So let's define K nth Milnor K group of a ring, of a local ring. Let's assume it's a local ring, which is the n degree part of this ring Km of R, which is a tensor algebra of R star as a Z module over the ideal generated by elements of the form A times 1 minus A, which A and 1 minus A should be invertible at the same time. And of course, we have the usual map from K2, the isomorphism from K2 of Milnor to K2 of, again, K2 is defined by Milnor, which can be given by, which is that second homology of EF. This can be given explicitly. This element of on the right, I will come back to that. One famous result is that Milnor K-group finite fields for n or greater or equal to 2 are 0. Of course, let's give a definition of K groups. I will be fast here. To any path connected CW complex, which it's a fundamental group has a perfect subgroup like N, we can associate another space. And there is a map from X to X plus, which it's a fundamental group of X plus is the fundamental group of X over N. And the homology of the new space is almost the same of the homology of the old space. And in a way, this space is unique of the homotopy. We call this plus constructions, and the K groups is defined as the higher homotopy groups. Ki is defined of the i's homotopy group of the classifying space of the plus construction of GLR. So, sorry, this is the plus construction of the classifying space of the group GLR as this is an abstract group. This plus constant is with respect to the elementary subgroup ER. We have the famous Horvitz maps from the KR to the i's homology of BGLR plus, which this is isomorphism to i's homology of GLR. And there is a canonical map between Milnor K groups and Koilen K groups. So we have the product structure on both K groups. And this product allows us to define a map from Milnor K group to Koilen's K group. So let's go to work of Nestor and Suslin, which be the base of our work. My work R. I will assume R is a local ring with infinite residual field. Then we have the this homogeneous stability, which starts from Hn. The nth homology of GLN is isomorphism. I put this subjective here. It's this is the first map is isomorphism to nth homology of GLN plus 1, and we can continue like that. And moreover, to Suslin to prove this, in fact, Suslin has constructed a map from Sn, like Sn to from nth homology of GLN to Milnor K, nth Milnor K group of R. such that the exact sequence you can see is the sequence that you can see is exact. So in fact, the kernel of S n is the image of natural map from n's homology of GL n minus 1 to n's homology of GL n. And also he proved that the composite of you can see from Milnor K n's Milnor K group to n's K group. Then we have the Horvitz to n's homology of GLR. Then we have the stability isomorphism, and then we have the map of Sustain. This coincides with the multiplication, but -1 to power n minus 1 times n minus 1 factorial. Very strong theorem, has many applications, and at least in the K theory, in relation to K theory. And to go beyond the stability which we have, Sustain conjecture that we have for infinite fields, we have this bijections. It means that from R homology of GLN to R homology of GLN plus 1, this map should be with coefficients in Q, in rationals. This map should be injective. There were few cases known for this work before the work of Galatius, Coopers, and Randall Williams. They proved this Susslin's injectivity conjecture for the case of when R is n, in fact. Not well, in this notation is n plus 1. So if F is any infinite field, K is any field such that n minus 1 factorial is invertible in K, then n's homology of GL n minus 1 with coefficient K injects into n's homology of GL n F with the coefficient K. The proof is difficult. They use the techniques that developed before in relation to infinity cells, and I'm not familiar with the techniques. I'm trying to read it, but still almost in the beginning. Moreover, what they did, they studied the relative homology group of n plus 1 to GLN, the n plus 1 homology of GLN and GLN minus 1, which now we know that is isomorphism to the quotient group of n plus 1 homology of GLN over n plus 1 homology of GLN minus 1. And this is the term they proved. They put some kind of they prove the natural structure. They look at this as they could prove that this is can be seen as a module over the Milnor groups, and then they prove that we can somehow generate these groups, and they use the third Harrison homology of graded rings, which is in this case Milnor groups. And what I'm not going, as I said, I don't know much about this work, but just mentioned here to go here that this suggests, the work suggests that this quotient group that we have, it has somewhat a complicated structure. So what I hope that the method can be used to be proved this conjecture in the place of a K that in coefficients, K field that n minus 1 factor is invertible, we can put Z of 1 over n minus 1 factorial. And this is, of course, this implies that, but I hope that the work can be applied in this situation also. So from now on, I assume that R is a local with infinite residual field. So the approach to prove the theorem of Galateus, Coopers, and random William up to work of them, of course, is like that. Let's Pn of R and K be the this map to shorten notations, be the nth homology of GLN minus 1 to nth homology of GLN, and let Qn be the complex that we can see from nth homology of R times 2 times GLN minus 2 R to nth homology of R times 2 GLN minus 1, and then we have inclusion map to nth homology of GLN R, which here alpha 2 is the usual inclusion, but alpha 1, what does, if you take a diagonal map of A, B with capital A, this substitute interchange the places of A and B. Back in time when I was working on the this Susslin's conjecture, I realized that there is a induction. Maybe I can prove this in by inductions, but for this we needed to that this complex Qn to be exact. So let K be either the ring Z 1 over n minus 1 factorial, or a field such that n minus 1 is invertible. So if Pn minus 2, if the map Pn is minus 2 and Pn is minus 1 are injective and the complex Qn is exact, then the map Pn is injective. So to prove that this, I used the I need a description, explicit description of the map from Milnor K, nth Milnor K group to nth homology of GLN, and I could really solve this, and I found what is its exact image, and this helped me to prove the propositions that you can see, and the theorem that Galateus, Coopers, and random William proved.
I couldn't see them. That was way too fast to see them. You said the propositions that we could see, but I didn't see them. You just skipped.
This proposition on the top. This is
the one you already talked about, but I didn't read the lower one. Does that say something else?
This is the propositions that the map, the composition of the Horvitz with the Cn, which is a map from Milnor K, nth Milnor K group to nth homology of GLN. This I needed to prove that the previous proposition. I needed an explicit map description of this map, which is written here. You can see. But C of A1 to AN, I will define what is this element in the homology, nth homology of GLN R. That's okay?
Yeah, thanks.
Okay. And Galateus, Coopers, random William prove that this complex is in fact exact. When K is a field such that n minus 1 factor is invertible in K. The proof, I found it very difficult. They use ideas out of my my knowledge. So, but when the proof appeared, I went back to look my notes from the past, and so I started to work on this problem again, and so this talk will be about those results. Okay, let me talk about this element C of A1 to AN. Let B G be the complex, the right bar resolution of a group G. So the nth homology of G with the integral coefficients can be seen as the nth homology of tensor of this complex with Z over ZG, integral group ring ZG. So if G1 to Gn are pairwise commuting elements of G, the homology class, which I show with this notation, represented by cycle that we have here. In fact, the homology class C1G, CG1, G2 to Gn is the cycle, is the element of nth homology of G represented by the cycle that you can see here. Just define it. So now I would like to study the kernel of a map from nth homology of GLN-1 to nth homology of GLNR, and the co-kernel of n+1 homology of GLN-1 to n+1 homology of GLN. So to do this, I came up in my competition. I came up with a complex made of minor K groups. You can see the complex here. It starts with the nth minor K group, and then we have from tensor product of R star to and n-1 minor K group of R. We have the map delta 1 and delta 2. Well, it's difficult to read it, but you can see it. The differentials are simple. If I pick an element like A1 times tensor to AI, tensor on element of n-I minor K group B1 to Bn-1, we just take sigma anytime we pick one I, we put in front of the in the symbol, including which is in front of the symbol of which is B1 to Bn-1. It's very easy. Just compute. One can compute. This is a complex.
Is there an interpretation of this complex as like, or like, does this complex exist for any graded ring, and does it measure like some sort of ring generators or something in that direction, like the homology?
I'm not sure. Can you ask again? Can you repeat?
Oh yes. So I guess my first question is like, is this a general construction that you can do for a graded ring with maybe a few other conditions, like, or using some other structure on Milnor K theory?
I don't know. I don't know. Well, I never thought that way.
And yeah, and then my next question would be like, you know, so Milnor K theory is a ring. There are a lot of invariants of a ring. Is it measuring something like the some Tor group associated to the ring, or indecomposables or something in that direction?
No idea.
Okay.
I haven't thought about the other directions really, but this is a complex that really popped up in my calculations, and at least the second homology of this, I think is interesting and related to those maps that you can see above. And of course, the first homology of this complex on the right is exact. It means the kernel of delta 1 is equal to image of delta 2. This is also, I think, is not coincidence. It does something with the homology of a general linear group. I will tell something about that. But let's define new groups. I look them as a general block groups, B and R. I put it 0 if n is 1. I put a new group B tilde of R. This is a group which is very close to BR. And if n is 2, and this and the kernel of delta 2 over image of delta 3 if n is greater than or equal to 3. And the B tilde here is the indecomposable case 3 of R over the Tor. We have a map from Tor of mu R to in decomposable K3. And I take the quotients. This is if characteristic of R is different than 2. Maybe this characteristic is not good notation here, but I need a condition for this case. And mu to infinity of R is infinite. What I wanted to say is that I have to assume in this remark, you can see that I have to assume that R, there is a map from R to F such that F is a field and mu R embeds in mu R, mu F, you can see. Okay, but what I'm interested in this is for n greater than equal to 3. So I look them, I see them as a higher version of block group. There are other higher versions defined by Zagier, Boncharovs, and others. They are more suitable application number theory. Let me talk about this. This maps K3 of indecomposable over the Tor that you can see. This comes from the block the theorem of Bloch-Wigner. Let WR be all elements of R star such that 1 minus A also invertible. We have the pre-Bloch group, famous, and we have this subgroup of it generated by this by these relations. And if we take R times tensor R times sigma as a group of R, tensor of R with itself over the subgroup generated by A tensor B plus B tensor A, then we have a map from pre-Bloch group of R to this group that we just defined, which takes a generator like generated by A to A times 1 minus A. This is a Steinbeck relation. And the Bloch group is the kernel of this map. And then we have this exact sequence. Of course, we have this Sustain's general version of a Bloch-Wigner exact sequence, which gives us, of course, this version of for local rings is mine, but I use some deep result of Suslin on this. So if we have there is a map from R to F, which such that F is a field, F is a field such that the mu of R is inject inside mu of F, then we have this exact sequence where, of course, the Tor of mu R tilde is the unique non-trivial extension of Tor. What I here maybe the easier way to say what is the B tilde is a extension of the Bloch group by Z2 when the when mu to infinity is finite and the characteristic of R is different than 2.
Sorry, I think I missed that. Can you say again what mu is?
Mu are the nth roots of unity of the ring.
And that is a ring then again?
No, that's not a ring, that's a group.
Oh, it's an abelian group. Yes, I see.
It's an abelian group, yes. And of course, this is the extension of B tilde, is extension of BR by Z2, and the map that we have from B tilde to the Bloch group we have comes from this this Bloch-Wigner theorem. And here K3 in decomposable, I defined it now, is the co-kernel of the map from K third minor K group to set K group. So my first result in this direction is that there is a natural map from Bn of a ring, these new groups, to the kernel of the nth homology of GLN-1 to nth homology of GLNR, and which its image is n-1 torsions. Of course, the coefficients here, I assume I pick z of 1 over n-2 factorial. This is important. If it's in place of yes, this is and its image is a torsion, and I can give an explicit map, but this explicit map appeared when I proved that this map. I constructed this map. I constructed it indirectly, but when I was proving it, this map, explicit map appeared. So what I can prove is that if the complex QN which I was talking before, be exact for n for fixed n, which is bigger than or equal to 3, and if PM, the map PMR is injective for m n-1, n-2, then Kn is surjective, is a surjective map. And of course, I can prove this for all n less than or equal to 4. And my conjecture is that the Qn is the following complex that you can see here. If n is greater than or equal to 3, then the complex Qn R with the coefficient in z of 1 over n-2 factorial is exact. So we know that this is true when we replace this coefficient ring with k, such that n-1 factorial is invertible there. But still, I believe that this version is also true. And so now let's go to this quotient of R's homology of GLN to R's homology of GLN-1. I'm interested to this quotient when R is n+1. And from the inclusions of the groups, which you see here, I can get an exact sequence. This is pretty direct. By studying this complex, I can reduce this to the when k is z of 1 over -2 factorial. Then I can reduce this. Some parts of the quotient group on the left can be, they go to 0, so I can remove them from the exact sequence, and that's reduced to this exact sequence. So to study the group of this quotient group, I give it this notation Hn of GL of R n+1. I have a reason for that I gave this name, but let's not talk about that. And we have this on the right, the bottom line. We have this quotient group of n+1 homology of GLN over n+1 homology of F R star times GLN minus of R. So what suggests this? This suggests that to study this group up to induction, of course, we should study this quotient group. And I show that this is related to the this higher block groups that I defined. So the first case is that in case of when n is 2, we have this isomorphism, the third homology of GL2 over the third homology of R times GL1 is isomorphism to B2 of R, the second, I call it, let's call it the second block group of R. And So this needs really to be proven. It's not easy to see directly, but again, I have a certain result of Suslin and myself. We can combine them and we can prove that this is an isomorphism. But what I prove in general is that if the map PM be injective for m equal n-1 in n-2, then there is a natural map from nth Bloch group, let's call it, to the quotient that I would like to study. The construction of this map also is not direct. So this is what I don't like about that, but I will explain how to do, how I did that. But if we use the work of Galitius, Coopers, and Random Williams, then I can remove and replace this coefficient ring with the field K such that n-2 factor is invertible. Then I can remove that condition of injectivity on the propositions. So then we have this map. But what I think about this map, why it's interesting, because I think it's injective. It's surjective, sorry. I think it's surjective. I prove that it's surjective for n less than equal 4. Of course, for and and so we have she's 3 and she 4, which they are injective. They are surjective. Sorry. So, and my conjecture that this map is surjective. I am not sure if it's isomorphism or not. I don't have any idea if it should be isomorphism. Well, the case n equal 2, here it's isomorphism, but I don't know if I can tell this for general case. But at least on the group of the group that appears on the right, this Haber group, we have something. We have this Milnor K groups, and we have the maps. One can do something rather than the group on the left, the quotient group on the left, which is hard to say something about that without having strong tools, actually. So let me construct the map Xi-n. Well, first I define the posets P of Rn. If S is a non-empty set, then we can construct posets, which is finite order sequence of distinct element of S like that, and we have a ordering on them. As you can see, this is the famous construction. So, and to any posets X, we can associate a space called its geometric realizations. And here the set S that I'm interested, I show it with SRN, is the set of all submodule of Rn generated by one element. And P and R is the subposet of sequences, is the subposet of O as SRN, is contained of all the sequences that you can see, x1 to xk generated, they are generated by x1 to xk, such that any two xij is a basis of a direct summon of Rn. So if R is a field, we just have to take them one is not the multiplication of other one. So, okay, it's easy to prove that this poset is contractible, and this gives us a complex, which the L of Rn is a free K module with bases consisting of L+1 tuples like this, and the partial operator delta L is just the alternating sum of phase operators, which throws away the ice component of the generator of generators. And if you pick a resolution, this is a very classical construction, so nothing strange here. If you take a projective resolution of Z over the group GLN of R, then and you can construct this double complex. And from this we get the first spectral, first quadrant spectral sequence E1, which converges to 0. And using some results, we can simplify this group's E1 PQ, and which finds the following form. What is interesting for me is that in particular, the E2 of 0 and Q is the quotients that we wanted to study, is a Q homology of GLN over Q homology of R star times GLN minus 1. So to construct Xian, we assume that we have to assume that N is greater than or equal to 3. And of course, let's put K as Z, the ring Z of 1 over N minus 2 factorial. First, what I did first, I constructed a surjective map from the nth block group to the E2 of 2 and N, this group of the spectral sequence. And this is the part that I have to work a bit. And then Xn is just simply the composition of a Xn prime with the second differential of 2 and N. And of course, I conjecture that for N greater than or equal to 3, some groups of this spectral sequence, they are 0. If we have this conjecture, which is a bit difficult, I don't know how to deal with it, but if this is true, we can prove 2 or 3 of the conjectures I just mentioned. From the higher block group to the kernel of this homology of nth homology of GLN minus 1 to nth homology of GLN, and also the map Xian. Both we can prove that they are surjective. So this is the construction. I got here, but well, during the study this problem, I could use the result of Galatis, Coopers, and random billion to prove some results, but this is direct, just follows from their results. It's, but I didn't see in their paper, so I said maybe good idea present it here. Let's P a prime F of infinite field such that F times tensor with Z over P is 0, okay, and the polynomial xp minus 1 splits into linear factors. Then they prove that these relative homology of GLN and GLN minus 1 with coefficient ZP is 0 in degree D less than 5n over 3. So, and of course, a corollary of this is that if P and F is as previous theorem, and if N is greater than or equals 3, K plus 1 over 2, then N plus K homology of the relative groups GLN and GLN minus 1 is uniquely divisible. So, and the kernel of a uniquely P divisible, just sorry. And the kernel of a N plus K minus 1 of a relative homology, the kernel of the N plus K minus 1 of GLNF with coefficients in Z to the same homology of GLN is also uniquely P divisible. Let me give a proof of this very short. In fact, by the previous theorem, we can see that we have these relative homologies which are 0. The first one, we have to assume that N is greater than 3K over 2. And for the third time, we have to assume that N is greater than or equal to 3K plus 1 over 2. It just immediately follows from the previous theorem. Now, the long exact sequence induced by this short exact sequence implies that the multiplication by P and the group of n plus k of GLNF, relative homology of GLN and GLN minus 1 is a bijections for n equal to 3. So this says that this relative group is Z over 1 over P module. And we can say the same thing about the kernel of the, now having this, we can say the same thing about the kernel of this map. So now we can prove that if F is algebraically closed, then the integral homology, the nth integral homology of GLN, the map from nth integral homology of GLN minus 1 to nth integral homology of GLN is injective in this general case, even with Z coefficients. And of course, using this, we can prove that the nth homology of GLN can be decomposed as a nth homology of GLN minus 1 and the minimal K group of F. And the quotient group that I just wanted to study, this is uniquely divisible for n greater than equal to 4. This is divisible for n for less than 4, but for the rest is uniquely divisible. And of course, we can construct a natural map from n's block group of F to these quotients. And of course, I believe that this is surjective, but this is if the previous conjecture I talked is satisfies, if the previous conjecture holds. The proof is again easy. This is trivial if n is n1 and 2, and this is true for, I proved it for n equals 3 in some of my articles. So let's assume n in one of my articles. So let's n is greater than equal to 4. Now, by previous lemma, the relative the n plus homology, relative n plus homology of GLN and GLN minus 1 is uniquely p divisible for any prime p. So it is uniquely divisible. And the same we can say about the kernel of the map from n's homology of GLN minus 1 to n's homology of GLN of F. So this is also uniquely divisible. But by the work of Galatius, Cooper's, Randall Williams, this kernel is torsion. So it must be trivial. And of course, by I, we know we have this isomorphism. But we have proved that the group on the right is uniquely divisible, so the group on the left also is uniquely divisible. And the case, the construct the map, because we have the injectivity for we have the I and 2 with integral coefficients, we can prove 4 also for integral coefficients. The same proves the same construction works here. So I stop here. Thank you very much for listening.
Let's thank Behrooz.
I don't know if I was okay. So it's almost the time.
Are there any questions or comments?
Oscar, I really didn't understand your questions really about this complex.
I think I asked. Oscar's question, or I asked a question about the Milnor K-theory complex.
Oh, for other K-theories.
I arrived a little bit late, so maybe I missed a question by Oscar, but all I was saying was I asked the question like half an hour into the talk, not Oscar.
Oh, you weren't. Okay, sorry. And I really didn't understand your questions.
Oscar proposed an answer in chat. If he wants to say that.
Okay.
So I think what Oscar said, which I think is the answer to the question, is that or one of your complexes looks like the bar complex, computing Milnor K-theory as a module over the tensor algebra over the something. What did Oscar say? We could also go to it just to look at it.
Oscar could also just explain it.
Yeah. Oh yeah, the tensor algebra on the units.
Yeah, it's easier if we have it on the screen, but
let's see. Let's
so the complex Q was defined.
Is complex.
Yeah. So if you add these together for all n, you can think of this complex as the bar complex for the tensor algebra on R star.
Okay.
That has a left module, which is just Z, I guess. And it has a right module, which is Milnor K-theory.
Okay.
Where R star, it acts by your formula for the differential, right? It acts by inserting AJ as the first element. So from that point of view, this complex has an interpretation. It's computing Tor over the tensor algebra on R star of Z with Milnor K-theory.
Okay. I didn't know this.
I think that's somehow what Jeremy was asking. It's answering the question, how do you build Milnor K-theory as a module over the tensor algebra on R star?
Okay. Good. Thanks for clarifying this for me.
And in a sense, what we did in our paper, the way it starts is by saying that you should maybe change the question, not to think about it over the tensor algebra, but to think about it over the symmetric algebra on R star.
R star. Okay.
I suppose, strictly speaking, it's the exterior algebra on R star. It's the graded commutative algebra on it.
I'm a bit confused. This is not the? Shouldn't this just be the Tor or the bar complex over R star, not over the tensor algebra of R star or something?
If you see, there's like
take the
tensor 2,
afterwards.
tensor n. You see the like R x with a circle 2. Oh wait, no. Yeah, no, I take that back. Now I'm agreeing with Peter. Wait.
I mean, except that R star is not a ring. So
precisely. I think that's my difficulty with what you're saying.
No, I mean, I'm not saying that it's not what I said, but I'm also claiming it's not what you said.
Yeah,
because there is a tensor missing.
Yes. Hard to compare Oscar's answer to a slide that I didn't have access to, but yeah, I don't. Is it like a Kazoo resolution? Is this?
It seems like still computing Tor, but using a Kazoo complex.
Yeah.
Okay.
Hi, Sander and Oscar. Welcome to our seminar.
Are there any other questions or comments?
You said you had a reason for using this notation H upper star and then like subscript GL.
Yes, we have this higher block groups, and from the co-kernel of from the group that I defined, there is a map to these higher block groups. So I took this notation from higher block groups. So there is a conjecture that this map from this group to higher block groups is surjective. So for this reason, I have the shape of this cohomology of a group rather than homology. because there is this other side to algebraic geometric side to it. And for example, the map that is, let me see where I came out of this. I'm not sure where I use this notations. Yes, from there is a map from this quotient group to the this higher block groups. It's higher Char groups. Sorry, to higher Char groups, which they are pretty closely related to this K theory, and there is a conjecture that this is surjective, and it's proved. And by Suslin's result, it's true for if R is n. And it's proof for Rn plus 1, 2 by Gerdes back in 90. And it's conjectured that this is surjective. So I took this notion from this higher block groups, which we have this map, and we hope to, if we have a certain result over these quotients, we can get information over these higher Char groups. So I took this notation from this groups, which is coming from algebraic geometry.
Maybe a more, can I ask a more general question in this sense that you mentioned a lot of conjectures, and I was wondering, what do you think is the most interesting or the most high level conjecture that like kind of guides you to what you are doing here?
Well, it's difficult to say that because they are related, but one doesn't really imply the other one. But what I think
and feel free to mention 2 or 3 if you need to.
Yes, let me go back to this conjectures. Because I have evidence for them. The conjecture that you can see here, this exactness of this complex, that we have a version of that proved by Galitas, Coopers, and random William. And but this is with a different coefficient ring. I think this is important because this would imply the 2 or 3 of the conjectures that I raised. For example, it will imply this injectivity conjecture. In the beginning, this conjecture, it would imply this conjecture, and it would imply. I think it would imply, I cannot find it. It would imply this conjecture also, but the other one, this one, and of course for this one, I can remove in this proposition, I can remove this condition 2, so it simplifies. But for the surjective of remains. So that conjecture I talked, it will be implied to 2 conjecture, but and it will simplify some of my propositions. But still, to prove the surjectivity of this, well, there is this spectral sequence and this conjecture about this spectral sequence. This would imply most of them. This conjecture, but it is, I think it is very difficult to deal with it because it is.
I guess this is the least high level or the lowest level in conjecture in the sense that it's the most technical.
Yes.
So yeah, I was wondering more about the guiding principles, and so the guiding question is whether these maps are injective and surjective, and that would imply that the Milnor K theory is 0 in those degrees. Is that right?
Yes, that's the main thing. Yeah, but as I said, I couldn't go much ahead with this, so I have to see. For example, I'm studying the block groups, high block groups. If they are, I can calculate some of them. For example, if there are rings that the K-theory are simple, the Milnor K-theory is simple. So, for example, for number fit, K-theory is 2 torsion, and here the higher block groups also are for fields, of course. There are also 2 torsions, and so in a way, I think these block groups are more manageable than the quotients on the right, and these sets of conjecture are related they are related. So, and it's difficult to put one above other for me, but one can imply other 2, as I can see.
Maybe I could ask you something quickly about your definition of the higher block groups, if maybe you could find that slide.
Yes, I go back to. Here.
Right. So for 3 and higher, they're defined as the homology of this complex Q.
Yes.
Doesn't that definition, don't they have a natural involution then, these higher block groups, by swapping the 2 R star factors? If you look in the definition of the complex in position 2, there's an involution by swapping the 2 R star factors. And
okay.
It doesn't exactly commute with the differentials, but it commutes up to sign. And so I think it still induces an involution on the homology in that position.
Okay.
I mean, at least it commutes with the differential. It commutes up to sign with the differential D2, right?
Mm-hmm.
If I have A1 tensor, A2 tensor something, and
yes,
you exactly get a sign. Oh no, maybe you don't get a sign because you don't have a sign in your differential. But maybe that's
I don't have. So
there's not supposed to be.
There is no need. You don't have to. Any
Okay.
sign will not be a complex.
Oh, okay. Well, then it's actually invariant under swapping the 2 factors.
Okay.
But it's just a bit surprising that it has a natural involution. Is that true for the lower block groups?
Lower. What do you mean by lower blocks for B?
This was only your definition for, I think, B3 and above. I think you define B1 and B2 in a different way, right?
Yes, B2, look, for this complex for n equals 2 is not interesting. It doesn't give much things. So we have to assume B greater than or equal to 3 when we want to define this in this way. We're using this complex, the higher block groups. For B2, I don't see any involutions. So
I don't understand why delta 3 commutes with the involution on the second thing that you are proposing. We also have to have an involution on the third part of the complex.
I think I just want to say that the image of delta 3 is invariant under that involution. I think that's the correct, yeah. From the point of view I was trying to say before, it's because actually Milnor K-theory isn't just a module over the tensor algebra on R star, it's a module over the exterior algebra on R star.
Yeah, okay.
And that's why you should get a, yeah. Interesting.
More
I
out
know.
there.
Any other comments? Yeah.
Oh yes, this is more out there question, but which rings do we think just in general should have slope 1 homological stability? And I guess there's an example of which ones don't. I guess there's the example of Z mod 2, but that's sort of a two torsion phenomena, and maybe that's a little special. Yeah, I guess like for fields, it's known that all but one of them does. I guess you have a conjecture about these local.
Oh, this the general version of covalence, you mean?
Yeah. I guess you have this. Maybe that was the first conjecture. It was a conjecture that wasn't related to proving things. It was just like oh yeah.
This conjecture, I mean.
Yeah, but like for number rings, which ones should have slope 1 stability? Yeah, or other ring, polynomial rings, etc. Is there a?
I don't know. I don't know any.
If there's
result.
any.
If you have a homomorphism to F2, you're not gonna get slope 2 or slope 1. Or at least without an offset.
Yeah, but I mean, I guess for F2, let's say with Z adjoint 1/2 coefficients, F2 has slope 1 stability, right?
Okay. What you are trying to do? You are trying to find other rings that has.
Oh yeah, I guess I don't know. I was just wondering what if there's like a general picture about which rings should have this slope 1 stability and which ones shouldn't.
Oh, that's one.
Yeah, was this conjecture?
I think it's difficult to go beyond this local rings. I think.
Recently,
general picture.
Peter, Sander, and I proved that for our Z Gaussian integers or Eisenstein integers, if you have coefficients where 2 is invertible, then you have slope 1 stability.
Still one step. Okay.
And so I was just sort of wondering, if there's that collection is kind of a little bit random. I'm just like wondering if anyone has thoughts on which rings should and which rings shouldn't have slope 1 stability.
I don't no idea. I haven't seen any results.
Okay, maybe let's thank Behrooz again.